this lab, we will further delve and expand the ideas of Newton's second law and relate it to the universal law of gravitation. We do so by determining the forces from motion of a star orbiting a black hole. Our main focus of this lab is to analyze the perpendicular and parallel components of the net force on the star. We will also estimate the mass of a black hole. From our previous labs and lectures, we know that F net is equal to the change in momentum over its change in time by the momentum principle. We can take this idea further and analyze its components and relate it back to the components of net force, the main focus of our lab. So, since every vector is equal to its magnitude times its unit vector, we can then apply the multiplication rule of calculus and obtain this equation here. And by using the ideas of curving motion, we finally obtain dp dt parallel is equal to its F net parallel, and similarly for its perpendicular component. Finally, in order to solve for the mass of a black hole, we know that the only force acting on the star is the gravitational force from the black hole. This implies F net is equal to its gravitational force. Now we have all the equations to solve for this lab. These calculations were all done on GlowScript. I will explain step by step the process I did to obtain the net force and mass of a black hole. So the first step was to set the initial conditions. I made my delta t to be the number of seconds in a day. And in order to obtain F net in its components, we need to first calculate the velocity and change in velocity, since F net is a function of its change in velocity. We defined before that F net is equal to this change in momentum over its change in time. We now have calculated F net. We will now break it up into its components. dp dt parallel is a change in magnitude momentum times p hat, and dp dt parallel is equal to its F net parallel. Since we have F net and F net parallel, we know that F net is equal to F net parallel plus F net perpendicular. By subtracting F net parallel from F net, we obtain F net perpendicular here. We are ready to run the code. The blue arrow is F net parallel is yellow, and F net perpendicular is purple. Since F net is equal to its gravitational force, F net will always point towards the black hole shown here. F net parallel is either pointing in the same direction as the object's motion or opposite to, depending on if the object is speeding up or slowing down. Here, the object is speeding up, so it's in the same direction as its motion. And when the object is slowing down, F net parallel is opposite to its motion. By using basic vector addition, we know F net perpendicular is here in purple. Here, in these two instances, we see something interesting. At these points, F net perpendicular is equal to F net, since F net parallel is 0. Since we have F net calculations, we can estimate the mass of a black hole. By using the universal law of gravitation formula and setting F net equal to its gravitational force, we can rearrange the equation and solve for the mass, as shown here. And below is how I calculate the mass of a black hole on GlowScript. Here's a snippet of data obtained after I ran my code. There was over 400 data points, and the mass of a black hole was not the same at each calculation. The average mass was found to be 1.65 times 10 to the 35th kilograms. And in order to understand what this means, I calculated its standard deviation, but since we're dealing with such large values, it isn't as intuitive to understand what this really means. This is where the coefficient of variation is useful. Here we see a low value, which means lower dispersion of data around the mean. Further, since the sample size is over 400, I was able to produce a confidence interval which allowed me to be 95% confident that the true black hole's mass is around this interval. Question 1. Discuss how the net force in its parallel and perpendicular components are different from the rate of change of momentum in its parallel and perpendicular components. Before, we stated that F net's components are equal to its dp over dt components. The only difference is in the way in which they are calculated. F net is equal to its gravitational force, so F net is calculated by finding its gravitational force using this formula here. We can further analyze F net by breaking it up into its components, which can be done by using basic vector addition. dp over dt is calculated by finding its change in momentum over its change in time. In calculating its parallel and perpendicular components was discussed in the beginning of the video. What if the black hole's mass you found was removed and a different black hole was placed in the same location and the star's motion was unchanged? Could you tell a difference? So we know the star's motion stays the same, which implies F net remains unchanged. Since F net is equal to its gravitational force, the gravitational force remains the same as well. And the formula for its gravitational force is shown here. This implies all of the values needed to calculate the gravitational force is exactly the same. Also, since F net is dependent on the mass of the black hole, this means the mass of the new black hole that was introduced is the same as the one before. So no, we could not tell a difference. Thank you.